Oh, I hope the other thing. Sometimes there's like a little manual switch for mute, and sometimes it gets flipped and I don't realize it, and then I'll have an entire lecture recorded and it's muted, and it's like no good. Okay, so it says there's 58 people with remotes. Well, I recommend getting the remote because I don't know, it's like a 5% free in your grade book, okay? So you can, if you do everything correctly, get 100% on everything, and you do the remotes, you'll get 105% in the class, and that can definitely help out those of you who are kind of, on the border between a few grades. So, so I definitely recommend that. And now, right now we're just kind of playing around to see if the system works, but starting next week, I'll start asking questions that I hope you find useful in your education, and also, well, the company says it keeps students engaged in learning, but I was hoping I was engaging enough on my own, but we'll see. Perhaps this is good. Okay, so so anyway, make sure you you register your remote via the CCLE thing, because I'm using their UCLA's own custom version of this program, which synchronizes with CCLE because it doesn't synchronize with the iClicker website. So so there you have it. Okay, 62 votes. I'm gonna stop this here, and then I'll take a look and make sure everyone's getting credit, and I'll once the systems can sync up, then I can kind of post the list of students who are registered, and you can make sure that indeed your remote is being counted. Okay, is that cool? How's everyone doing? Good? We all had a decent enough weekend, I hope. Any questions from chapter 2 or chapter 1 for that matter before we go on? We're okay? We're all good with dot plots and histograms? You guys have such lively expressions on your face. Anyway, all right. Well, let's get into chapter 3. Oh, here. Oops. Let me. That's not this class. Okay. So tomorrow, you guys are in the computer lab, right? And you have a lab. So here's the data that you'll use, and don't tell people I'm doing this. I mean, you guys know, but so I'm just posting the lab on here, and you shouldn't need to print this out, so you can just kind of look at it on there. You don't need to buy the lab manual. If you have the lab manual, you have your paper copy, but if you don't, you can just look at this here, and this should have the contents of the lab. And what you'll do in tomorrow's lab is the TA will work through the lab with you guys, and you will save your lab report as a PDF, and you will submit it here. You know what? I just realized when you guys submit it. Well, I'm not sure. Okay, I have to play around with this thing. I don't know if it'll separate you guys by TA automatically, or if I have to create 4 separate. How does it work in your other classes? Do you have like 4 separate things to turn in for each section? Yeah? Or is it just like, okay, so I'm gonna have to create 4 things for each section. Okay, I will do that then. Note to self, turn editing on. Let me, I'll delete this and I'll do it for section, 1, 2, 3, 4, or A, B, C, D. Okay, all right, I'll fix that. Okay, so let's get into chapter 3. Okay, chapter 3 is all about numeric summaries. Okay. All right, so a numeric summary, basically, so the big picture statistics, okay, we have a population, right? This is our big picture. Population, this thing is too big. We can't observe everything in the population, so we take out a little piece. And this little piece we call a sample, all right? And ideally, what can we say about the sample? The sample is ideally representative of the population, and that way when we make conclusions based on our sample, we can generalize those to the population. Okay. Now, what numeric summaries is all about is how do we describe the sample? Okay, so our sample, perhaps there are 500 people in the sample. Okay. And, hope they represent the population. Okay, so 500 people is still a lot of people, okay? How can we describe these 500 people? Okay, so first of all, we have to, we're going to have some kind of variable that we will use to describe, okay? So maybe we are just looking at one aspect or one variable. Maybe that aspect is age, okay? So we have some kind of numeric variable, all right? So we have a numeric variable. And so maybe the aspect that we are looking at for a sample is age, okay, measured in years. Okay. How can we summarize the ages of 500 people, okay? Well, we can list off every single person. We can draw a few, we can draw some graphic displays, right? So what are the graphic displays we can use for a numeric variable? A histogram, what else? A dot plot, okay, thank you, yes. All right, so to, kind of, to summarize our 500 data points, okay, we can display them with a histogram or a dot plot. Okay, but perhaps we want to compare sample to sample, and we can use dot plots and histograms to compare one sample to another. Okay, and that part of your homework in chapter 2 dealt with that. Have you guys done your chapter 2 homework and worked through them? Okay, I will post up the answers to chapter 2's homework so you can kind of just check your work and make sure you get the hang of it. You can always ask me questions or the TA's questions during office hours and whatnot. I'll have my office hours posted on CCLA, by the way. I'm sorry, I've been trying to figure out the scheduling for all of that. Okay, so to summarize that, we can display it with a histogram or a dot plot, okay? We can also summarize these 500 data points with just a few numbers, okay? And that's the idea behind numeric summaries, okay? So we can use numeric summaries to summarize the data values in our sample. Okay. And And depending on the situation, we might have kind of a custom numeric summary, all right? So for if we wanted to compare one country or one nation to another nation, we can describe kind of its overall economy with something like GDP, gross domestic product, okay, which is supposed to be the total value of goods and services produced by the country. And that can kind of measure how strong a nation's entire economy is, all right? And so you can say, the USA has this GDP and it's huge, and this tiny little country over here has this GDP and it's not that big, even though there's lots of people that live there and stuff. And so, you have different numeric summaries. It's the NFL playoffs, and so a lot of times at the end of games, they will give the quarterback a passer rating, okay, which is basically a single number that tells you how good of a performance the quarterback has, okay, or had during the game. And so they might say, part of the reason why this team lost was because their quarterback performed poorly and his passer rating was this, and it was this number. Meanwhile, the other team had their quarterback performed very well, and his passer rating is this, okay? Now, it's a single number that just is supposed to capture the entire performance of a game. It doesn't tell you the details of each play. It doesn't tell you whether the teammates were doing a good job or bad job or whatever. It's just a single number, but because it's a single number, it's also easy to compare. So it's a double-edged sword, these numeric summaries. They summarize lots of data. They get rid of a lot of detail, which is both a good and bad thing. The information that you have is not being cluttered by all of this other stuff, but at the same time you lose a lot of detail, okay? There's a numeric summary that you guys are probably all familiar with, and that's your GPA, okay? So if you think of your high school GPA or even your GPA here at UCLA, that single number is supposed to summarize your entire academic career, okay? So how well have you done in all of your classes? It boils down to a single number, and it doesn't tell you any details. Maybe you had one quarter where just a whole lot of stuff was going on in your life, and so you performed poorly, and that brought down your GPA. Well, the GPA as a numeric summary doesn't capture that. It doesn't tell you your life story. It just says, 3.8 or 3.2, whatever, 2.3, whatever it is, okay? It's just a number. It just says, this is the numeric summary. And that's what we're doing here, okay? From a population, we're drawing a tiny little sample, and we're just going to boil this sample down to like maybe one or two numbers, a few summary numbers. And we can kind of compare one sample to another. Maybe we have another population with another sample. These summaries, we can use them to compare samples, all right? To summarize the data values in our sample, okay? Numeric summaries are especially useful when comparing data from one sample to another. From one sample to another sample that may or may not necessarily be drawn from the same population. Okay. Okay. So summaries basically boil all your data down to just one or two numbers. Is that okay? Can I flip to the next slide? I saw 2 people nod their heads, so, and everybody else seemed unresponsive. Okay. All right. So, so like I said, we have, depending on the situation, we've got different numeric summaries. GDP, GPA, passer rating. These are all, examples of numeric summaries. Okay. GDP, passer rating, GPA, or just, anything you can think of that basically summarizes everything down to a single number, okay? And we also, so these are kind of specific for certain situations. And because, because we all, we're used to the American GPA system, we have an intuitive sense of what a good GPA is and what a poor GPA is and all of this, okay? But if you're from another country where the GPA system is very different, the way they evaluate school, these numbers are not as useful, right? If you go to Germany, the way they give marks in classes is different, and the best GPA you can get would be like a 1.0, and so if you're not familiar with that, it's not as useful, okay? But we have numeric summaries that kind of just fit almost any situation, okay? And so we have summaries to measure center. And this is the mean and the median. These are ways we can measure the idea of center in a set of data. Okay, and we have summaries to measure spread. And these are things like the range, the interquartile range, the IQR, and the standard deviation. Okay. And our book separates these and say, if your data has this shape, these are the measures that are preferable for this data. And if your data has this shape, these are the measures that are preferable in that situation. The truth is we can calculate the mean and the median for any shaped numeric data. And we can calculate the range, IQR, and standard deviation for any shaped numeric data. But the book does have a point in saying we might prefer these measures of center or spread in these certain situations, okay? So in situations where our data is symmetric, it may be preferable to use mean and standard deviation. Okay. And in situations for skewed data, prefer to use the median, range, and IQR. Okay, but these are just preferences, okay? The truth is these can be calculated for any numeric data, any shape, okay? I'll say, okay, so just a quick check. True or false, if a data distribution is skewed left, we are likely to have outliers much larger than the rest of the data. True or false? False, okay. So skewed left, we're probably going to have outliers that are much smaller than the rest of the data. True or false, you can, with symmetric data, you are unlikely to have outliers. That's also false. Symmetric just means if you have outliers that are larger, you're going to probably have outliers that are smaller, but it doesn't mean you are more or less likely to have outliers. So symmetric just means whatever happens on the upper side, you're going to have happen on the lower side. So if you got outliers up here, you're going to have outliers down here, but not necessarily that there is or is not outliers. Okay, so let's we'll talk about the mean and the standard deviation first. That's probably what we'll get through today, and then on Wednesday we'll talk about the other ones. Okay. So the mean. This is I think we're all familiar with this. This is so at its heart it is a measure of center. Measure of center, or a numeric summary, that describes where, and this is kind of the key that we are pushing here, describes where the balancing point of our data is. That describes where the balance point of the data is. Okay? And symbolically, we write the mean is x bar, and the formula for x bar is that we add up all of the x's and divide by n. This just says add up your data points, add up your values. This is a summation sign. Do I have to define all of these things? I don't know. Okay. Yes. If you don't like formulas, don't bother with them, okay? So this thing that looks like a sideways M or an E, this is a sigma. If if you're familiar with the Greek alphabet, sigma is kind of like the capital S, and that means summation, which means add up all of your values x, and then divide by how many values you have. Which is n, the sample size. Okay, and so throughout this class, if you see x bar, that means the sample mean, okay? And if you see n, that is your sample size. All right, so that's simple enough, right? I think we're all familiar with this. We probably learned this in like 6th grade or something. Here's, several numbers. Let's just imagine a family of 4 kids, family with 4 children, and the ages are, what are the ages of these kids? We have 16-year-old, 14-year-old, 12-year-old, and a 9-year-old, okay? What is the mean age? The mean is we add these up, and then I divide by 4, okay? So 16 plus 14 plus 12 plus 9, that equals 51. 51 divided by 4 is 12.75. This is our mean age, okay? Now, this idea of a balance point is I could draw a number line, okay? And let's see. So let me just say 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. And I'm going to draw dots where our children are. So we have a dot at 9, a dot at 12, a dot at 14, and a dot at 16, okay? So if you imagine this as some kind of seesaw, where do we want to put the fulcrum? The fulcrum goes at 12.75. It goes right here. This is the mean. This is our balance point. Okay. Conceptually, are we cool here? All right. And so the reason why we might say the mean is preferable for symmetric data, okay? So think of, let's think of some skewed data here, okay? So let's have a skew, okay, well here's a silly situation. Okay, so let's imagine we're at a diner, okay, in a small town. Small town with the oil boom, right? And right now oil prices are low, and so these are like ghost towns now. Like, you know, in like Nebraska, they're fracking for oil. Okay, so anyway, let's say there are 6 people, okay? And we go in and we say, how much money do you make, okay? So they say, oh, I make 65,000. This other guy says, I also make 65,000. And the next guy says, yeah, I'm right with them. 65,000. And 1, 2, 3, 4. Let's just, I'm tired of writing numbers, so we'll say 5 people. And this guy, he makes 70,000. How did that happen? Oh, I came here 6 months before you guys did. So I make more money. Okay, so what is the average income or the mean income? Okay, we would do 65 plus 65 plus 65 plus 65 plus 70, divide by 5, and I think that's 66. I don't know, something like that, right? 65 times 4 plus 70 divided by 5, yes, 66,000. Okay, so this is no surprise to anybody. This is okay, right? Let's say Bill Gates walks in. Okay, how much does Bill Gates make each year? Huh? A lot? Probably a lot, right? I actually have no idea. So let's just make it a nice $10 million a year. He probably makes more than that, okay? Or less, I have no idea. What's his official title anyway? President of the Bill and Melinda Gates Foundation. All right, so now there's 6 people, and what is their mean income? So we write, 65,000. So if the sum is now, what is it? 10 million plus, here, wait, 66,000 times 5. Okay, so if I add everything up, I get 10,330,000. Okay, and then I divide now by 6. And we get the average, the mean income is 1,721,666,067 cents. Okay, so this is now the mean income of wages in the diner. All right. Would you say this is an accurate representation of center? Okay, probably not for our data set, right? This is, because of Bill Gates, our data is now this sample is now highly skewed right. Okay, so this is, no longer representative of typical. Okay, it is the mean of that diner, and it's not incorrect to say that this is the average. Okay, however, because the data is so skewed, perhaps we would not prefer to use the mean. Okay, and so we have to keep in mind the mean is sensitive to extreme points. Or outliers. Okay, so if you got outliers in your data or you've got skew in your data, the mean gets dragged out in the direction of the skew. Okay? Okay, so that is why our text might say the mean is preferable for situations where our data is symmetric. Okay, but can you calculate the mean of skewed data? Yeah, we just did it right here. Okay. All right. Is that okay? Talking about the mean. All right, so let's talk about the standard deviation now, okay? The standard deviation, on the other hand, is a way for us to describe the spread in our data, okay? Okay, this is a numeric summary. That describes the spread in our data, okay? So what do we mean by spread, okay? So let's imagine two families of kids, okay? Two families, both of them, okay? Both have 4 kids. Okay, and the mean age of kids, we'll say, is equal to 12 years. Okay, so this is family 1. So family 1, we will say, I don't know, I need a last name. The Johnson family, okay. 4 kids, mean age is 12 years, so we will say their kids are aged 14, 13, 11, and 10. Okay, these are the 4 kids, and if we calculate the mean age, indeed we would get 12 over here. Okay, family 2, they also have 4 children. This will be the Okay, and let me do some math here. Okay, the kids are 21, 15, 9, and 3. Okay, and I'm pretty sure if I did my math correctly, and I divide by 4, yeah, the mean age is also 12. Okay? So it would be, I think we would be missing a lot if you said, oh, these two families are practically the same. They both got 4 kids, and the average age of the kids is 12. Both of those statements are true, but do those statements capture the entire picture? No, right? The picture at the Johnson family is very different, right? You got 4 kids that are very, fairly close in age, so, you don't have a whole lot of difference. But in the Smith family, it's a very different picture. You've got a 3-year-old running around at the same time as a 9-year-old, and someone in high school, 15, and a 21-year-old. So maybe this person's off to college. Who knows? Okay, this is very, very different. All right, so it is not enough to say, both families have 4 kids, and the average age of kids is 12 years old. Okay? There's another aspect, which is the spread. Okay? Okay, so another key aspect is the spread in our data, okay? And so the Johnson family has low spread, okay? Meaning most of the ages are well, in this case, all of the ages are fairly close to each other, right? Okay. And with the Smith family, has high spread. Okay, the ages are quite different from each other. Okay. And so, this concept can be applied to any data set, any numeric data set. We can talk about this idea of variation or spread. Are the values quite similar to each other? Okay. So if you think of, ages think of your 10th grade English class, okay? And you think of the ages of students in your 10th grade English class, okay? They're probably, not everybody has the same age, but they're all very close, right? They're all probably born in the same year. Maybe you have a kid who was held back, or maybe who is a kid who is advanced for his age. But in general, everybody in that class, very, very similar in ages, okay? And in this class, we're going to have a little bit more spread, okay? You have, first-year students and also fourth-year students or fifth-year students. So you're going to have a larger range of ages in this thing, okay? And then just think of, maybe if you go to a busy supermarket, okay? What kind of range of ages will you see there? You're going to see a large range of ages, okay? A large spread, because you got little kids going along with their parents. You also have old people shopping, and then you've got middle-aged people and young adults. You're going to have a large range. And so if we looked at the standard deviation is just a numeric summary that describes the spread in our data. It's just going to take this idea of low spread or high spread and assign it a value, okay? And so the concept for standard deviation, and I think this is what all we'll have time for today is the standard deviation can be thought of as the square root of the variance, okay? And the variance can be thought of as quote unquote the average squared distance from the mean, okay? And it's going to be quote unquote the average of the squared distance from the mean, okay? So let's look at the Johnson family ages. I already forgot. What were their ages? 14, 13, 11, and 10? Okay, so we decided, or we established that the mean is equal to 12, right? Okay, so what we're going to do is we're going to find the distance from the mean for each of these data points, okay? So basically, just subtract 12 from each value. Subtract the mean from each value. And you can keep the sign, you don't have to, okay? So how far is 14 from the mean of 12? It's 2 units, or 2 years away. What is 13 from 12? 1. 11 is 1 unit away from 12. And 10 is 2 units away from 12. Okay, so this is the distance from the mean. Okay, the variance, we can think of it as the average of the squared distance from the mean. Okay, so what is the squared distance? Is now we just take the previous numbers and square them. So squaring them is multiplying it by itself, not square root. Okay, so 2 squared is 4, 1 squared is 1, 1 squared is 1, and 2 squared is 4. Yay, so far so good? Okay, all right, and then so when we say the quote-unquote average here, the average squared distance then is going to be equal to, add them up, and instead of dividing by n, we're going to divide by n minus 1. And this is a weird thing that we do, and it's known as Bessel's correction, but we're just going to say add them up, and instead of dividing by n, you divide by n minus 1. Okay? So that's why I have the average in air quotes there, or just quotes. All right, so what is the quote average in this situation? So we would do 4 plus 1 plus 1 plus 4, which equals 10, and then we divide, instead of dividing by 4, we divide by what? 3, and we get 3.33. Okay? So this is the average square distance from the mean. This is the variance. The variance is equal to 3.33. And the standard deviation, which we call S, is a square root of 3.33. Square root of 3.33333 is 1.8257. And that is the standard deviation of ages in the Johnson family. Okay? We've got 2 minutes. I think I can do it really quickly for the Smith family here, okay? So the Smith was 21, 15, 9, and 3, right? So, so keep in mind the standard deviation here is 1.8257. For the Smith family, we had 21, 15, 9, and 3. The mean is 12, so our distances will be 21 minus 12, so 9, 3, 3, and 9. The square distances will be 81, 9, 9, 81. And then the quote average will be the sum of these, so 81 plus 9 plus 9 plus 81. And we're going to divide by 3 rather than 4. So I get 60. Okay, so my variance is 60. And so my standard deviation, S, is the square root of 60. So I have to 7.746. Okay, so we can see that indeed the standard deviation of Johnson family was like 1.7 something something, and standard deviation of the Smith family is 7.746. So, so this reflects what we already knew about the ages, that there is more spread in the ages of the Smith family than the Johnson family. Okay, we'll see you guys on Wednesday.